Hi, this video is a part of a series of videos explaining different subwoofer techniques. In this one, we will discuss the straight lines and the arc lines of subwoofers, the typical configuration of subwoofer that goes in front of the stage. And the very first thing to understand the straight line, we will do a straight line of subwoofers. But first we need to understand how the interaction with two adjacent subwoofers will change the directivity. And then how the length of an array of subwoofers will also changes the directivity in the system. As soon as we understand straight lines behavior, we will discuss subwoofer in an array line arc configuration that we have to understand as a section of a circumference. And every circumference has a focal point that is in the center of the circumference and has a radius that is distant from the center to the edge of the circle. In this case, in the edge of the circle is where the subwoofers are being deployed. And we will see how focal point and radius has tremendous consequences in the directivity of the subwoofer array. Then we will explain about the directivity angle and the effects in the frequency response. In other words, the more we have changes from a straight line to an arc of subwoofers with very short radius, we will have more dramatic changes in the frequency response. Then we will explain that the angle of directivity, in other words, the section of circumference that we will have effects also in the SPL, in the level of the sound, and this means that a straight line will have different SPL level as an arc system, let's say with a 60-degree arc design. And the last part will be summation of the subwoofers in the near field and in the far field. We will see how the subwoofer system will have better summation in the far field and lack of summation in the near field. In order to explain this, we will use this simulation software. It's called Map 3D. And to explain, we will have 4 different windows. One window is called isometric. The isometric is giving us a perspective like we are not exactly in the front or in the side or in the top. If we want specific information from being in the top, it's called plan view. This is like if we have a camera in a drone and the drone is flying and we can see the venue. We will have another visualization that is called front. Front is like we are like, in this case, we are here in front and we are watching to the direction of the stage. This area that we can see in the top display that I am moving the cursor, this is this section that is pink color that we can see from the front. This is where we are interested in see the color variations, in other words, the level variations from left to right. And this is exactly at 30 meters distance. And the last of the windows, the bottom right, is called section. This is a visualization from the side, like being here in the side, and we will watch all the way to the left, to the right. This means to the back of the stage and to the last person in the venue. So this means that if I am here in the bottom right, this is the stage and this is the audience area. This area that is pink color here, it is this line that we can see in the top right, that is the plan view. Okay, so I have here several examples for this explanation, and the first one is the straight line. In this straight line we have 8 subwoofers. Every one of these subwoofers is patched to a processor channel. So if I come here and see, let's say, the subwoofer in the center is this guy, and if we want to see the properties, we can see that it's patched into a processor to a channel called all subs. This is the channel, all subs and all the subwoofers that will go to this, that is the channel 1 in the processor. So let's see all the subwoofers. You can see this one, all subs, this one is all subs, all subs, all subs. Every subwoofer goes in the same channel. So, and we can see here that the yellow sphere or yellow bubble is changing position. Okay, if we select only one of these guys and we do a simulation, we can see that in this simulation, we can see that the level that is represented by color variations, it's being identical in a circular way. Let me change for the explanation to be relative attenuation. So in this case, the more bright red represents 0 decibels of attenuation, that is the maximum level, and then goes in the direction of the dark blue is 42 decibel of attenuation. We have every color is a width of 3 decibel range, so we need 3 decibel to change to the next color. We can see here what is the area by watching from the front, the area that is in the 0 to minus 3 decibels, and then the minus 3 to minus 6 at 30 meters distance. And we can see the level variation from being very close to being very far. Being very close, we are in the maximum level, 0 decibel of attenuation, and being very far, we are having around 39 or 40 something decibel of attenuation by the propagation of the sound in the air. Okay, having said this, the next thing that we will explain is that we will have 2 subwoofers right now. Every one of these subwoofers is being spaced by 2.5 meters. So the next thing to understand then is that with 2.5 meter distance between 2 subwoofers, these represent one wavelength at 136 Hz, represent half wavelength at 68 Hz, and represent 1/4 of wavelength at 34 Hz. So one wavelength is the same as 360 degree or 1 cycle. Half wavelength is the same as 180 degree of half cycle, and 1/4 wavelength is the same as 90 degree or 1/4 of cycle. So in 1947, it was published the second edition of a very famous book called Acoustical Engineering by Harry Olson. And he is explaining what happens when you have 2 separated sources. And he is telling you the pattern according to the proportion of distance to the wavelength. It says if you have 1/4 of wavelength, then you will have more level in the front and less level in the sides, and it will have a kind of oval shape, kind of egg, if we can figure out that is 360 degree drawing, but it's only showing half of the sphere. If we have 180 degree distance, we will have lateral attenuation, while in front we have summation, and we have one wavelength. We can see summation in the front, but summation in the sides, and we have an area that is a lot of attenuation. So if we do this in this simulation software, these 2 speakers, and we come to the frequency that says 1/4 of wavelength, 34 Hz. The closest frequency here is 31. Let's see what happens. You can see that now it's not a perfect circle as when we play with one speaker, but it's a kind of oval shape. This thing that we see here, it's similar to what we have here if we tilt this. So this means that we are watching a section of this, and here is like we are watching this section. According to this, to be half of the wavelength is 68 Hz, the closest to that will be 63. So if we select the same 2, you can see the lateral attenuation versus the frontal summation. The lateral attenuation is because the distance between these 2 speakers is 180 degrees apart by distance, and this produces attenuation, while in the front and back we have summation. This is what is represented in this second graphic. At half of the wavelength you have frontal summation and lateral attenuation. And then, according to this, if we have 1/4 of the wavelength, a full wavelength distance, This is 136 hertz. The closest frequency will be 125. We will see that we have summation in the front and lateral summation, and we have an area of attenuation between the front and the lateral. It is the same as this illustration that I am showing here: frontal summation, lateral summation, and an area of attenuation between the frontal summation and the lateral summation. So it's important to understand that the interaction between two speakers will cause this. But now look at this. If I select one speaker, but instead of B1 versus the adjacent one that can be this or this, I select this one, now the distance between these two speakers will not be 2.5 meters, will be 5 meters. And this will mean that in these frequencies everything will be shifted. So this means that with 5 meter distance, one wavelength will be at half of this frequency, and quarter of wavelength will be at half of this frequency, and half will be at half of this frequency. So if I want to make half, this will be then, the frequency will be 34 hertz. So now with this separated by 5 meters at 34 hertz, we will see a cancel. In this case, the closer frequency is 31. We can see the cancel because this distance produce cancel to a lower frequency, because increasing the distance by 2 is the wavelength of half of the frequency. So this means that every different possibility that we can have now, this one versus this one, it is this is 2.55, 7.5 meters. 7.5 meters, if I do 340 over 7.5, this is the wavelength of 45 hertz. So this means that in 45 hertz, we will see the pattern of one wavelength. That means this one. So come here and play the closest frequency, 40, and you can see that we have summation in the front and summation in the lateral. So what happens when we have a full array? When we have a full array, then the interaction of all the speakers will produce lateral attenuation, but will produce frontal summation. By the way, if we come back to this book of Harry Olson, in the page after the explanation of two sources is the explanation of a straight line source. And in this one, he is showing the directivity according to how large is the array versus the wavelength. And this guy says that if the wavelength is this one wavelength, we have this pattern. If we have two wavelengths, it's this pattern. If we have 3 wavelengths, is this pattern. 4 wavelengths is this pattern. 6 wavelengths is this pattern. So now what we have to understand is that our array measures 17.5 meters. Why? Because we have 8 elements separated each one by 2.5 meters. So this is 2.5 multiplied by 1, 2, 3, 4, 5, 6, 7. This is 7 spaces. Then 2.5 multiplied by 7, you can see 17.5. This is what it says here. So the distance, the length of the array, or the distance from the first element in the left to the last element in the right, is one wavelength of approximately 20 hertz. This is 2 wavelengths of approximately 40 hertz. This is 3 wavelengths of approximated 60 hertz, 4 wavelengths of approximated 80 hertz. So if we see this, the directivity, in other words, when we compare in the directivity the level in the front versus where it is 0.5, because this graphics is linear, is not in decibels. So in linear, 6 decibel of attenuation is 0.5. So here in 0.5, if we continue in this direction, we arrive to the position that is 36 degree. 36 degree in one side and 36 degree in the other side is 72 degree. So with 72 degree is exactly the directivity when the array measures one wavelength. If the array measures two wavelengths, then the directivity is 36. If the array measures three wavelengths, 24, the array measures four wavelengths is 18. So this means that if I measure 20 hertz, we will see 72, but 20 hertz is outside the bandwidth of the subwoofer, so we have to start with 40 hertz. And what we are watching here is these lines that you see here. It is the 36 degree in one direction, and this is 36 degree in the other direction. So this means that if I measure 40 hertz, and if we compare the colors, we can see that exactly where we have the center of this color, we see 3 decibels here, and we see here another 3 decibels. So this is 6 decibels of attenuation. From here is 3, and this is 6. So then the 36 degree is the largest arc, and this is the display angle for that frequency. According to this, now 24 degree will be at 60 hertz. So if we go to 60 hertz, then the 6 decibel of attenuation will be in the one that says 24. This one versus this one. So in these lines, it is where we can see two color changes. So if I am now here, this is 0 decibel, minus 3, minus 6, and we can see the color change. 0 decibels, minus 3, and minus 6, you can see the two color changes. And according to this, for wavelengths, it is at 80 hertz, it will be 18 degree. So, what is the frequency? 80 hertz. So then, if I show you, this will be this one versus this one. These two guys is the one that is the narrow coverage, the 18 degree. And if we test now 80 hertz, 80 hertz is the one that will show two color changes to the first line. So this guy to this guy, sorry, this is 63, 80 hertz. So now gets more narrow, and you can see this is 0, minus 3, and this is the minus 6. 0, minus 3, and this is the minus 6. So the higher the frequency, the system gets more narrow in the directivity. So this is the way the straight lines work. Also, to understand this behavior, let me do this. I will have a microphone here exactly in the center. This is in the center. And I will have a second microphone, and in the second microphone, we will be moving to different positions. So if I am in this position, this is the approximation, I think it's better. This is the approximation of the directivity that we will have when we are at 40 hertz. So let's do this. Let's measure with the microphone in the center using the analyzer. So this is the analyzer, but let's measure only, compensate the time, and I have to explain with the analyzer. This is the frequency response of all the system, the 8 speakers. And this is equalization that we are using in order to make that the roll-off that looks so rapid to be more even. And this is in order to make that when we test only one speaker, one of the central speakers, in this case, this is one of the central speakers, the frequency response is perfectly flat. So the response of this model of subwoofers before the equalization roll off this way, but now you can see that is flat. So now testing all the speakers together, of course that the level increase, but increase more in the lows compared to the highs. Let me store this and says this is the 0 degree position. What happens if now when we have this 0 degree position, let me see why the level, something in the level, I have here modification. Okay, so this is 0 0-degree position. And now let's go to the microphone that it's called aux, and the aux is the microphone that we are moving here outside. You can see that when we are moving this microphone to the outside, the frequency that shows the most attenuation, it's around the frequency between 40 and 50 hertz. This is the attenuation in that. However, if we put the microphone more here, this is the one that is closer to the second frequency here, the 60 hertz. So then if we come here, now you can see that 60 hertz is showing the most of the attenuation. And if we put the microphone in the next line, so the next one will show the most of the attenuation around 80 hertz. Let's come here and see here. So now the most of the attenuation, it's around the 80 hertz around here. So this is showing the most of the attenuation. And this means that if we want to understand lines of subwoofers, if you want to be in the directivity of for most of the frequencies in the bandwidth of the subwoofer, what we need to understand is that if we are in front of one lateral subwoofer and the other lateral subwoofer, that is this one, the people contained in this area is the people that will be in coverage of the system. So in order to show this, I am having microphones at different distances. I will have a microphones at 5 meters in 4 positions, from the central position to going to exactly the in front of the last subwoofer in one of the sides, and then outside and outside. Then 40 meters later, from 5 meters we move to 45 meters, so 40 meters later, and we have microphone in the center, a second microphone that is in front of the last speaker, then microphones that are outside the last speaker. Then we go another 40 meters more, this is 85 meters, so 5 meters, 45, 85 for this explanation, and then the last microphone is like in line with the last speaker, and then this is outside and outside. So what I want to show you is that if we have the array, and if we test the array in the 5 meter distance, let me compensate this and says 5 meters center. Okay, and recall here. So the microphone next one is the one that is in the limit of directivity, is the one that shows that is having attenuation. And what happens when we go after that? If we go after that, what we will see is that we will see comb filter. So all of these things that you are watching here is comb filter. If I go to another frequency, you will see all these things dark is comb filter. If I go to another frequency, then we will see comb filter. This comb filter, it is what we see now. In this position, you see dramatic attenuation, and this signature represents comb filter. And this is the last microphone, the one that is here, and we can see a strong comb filter. If we go to the microphone at 45 meters in the center, this is not comb filter. So let me do store and write 45 meters center. Put it here. And what happens if we go to the microphone that is around the limit of the directivity? Well, you can see it's still not comb filter, but we have powerful attenuation around 80 hertz. But if we go outside that, comb filter. And if we go to the last microphone, dramatic comb filter, this dramatic comb filter, it is what we see by all these dark colors. Then, if we go to the microphone that is at 85 meters, let's store 85 meters in the center. Okay, and recall here. What happens if we go to the microphone that is in the limit of the directivity? That is this guy. It is here, and we can see that we don't have comb filter, but we have more attenuation in the higher portion. As soon as I go outside that, then we see dramatic attenuation, that is the comb filter. Okay, and what may happen if we use a microphone that is exactly lateral to the array? In other words, exactly lateral to the array. Well, what we will see is comb filter. This is comb filter again. So then straight lines produces the directivity because in front of the system, all the individual speakers travel similar distances, and the relative phase by trajectories is so small that they have summation. But when we go outside the last subwoofers in every direction, the trajectories are so different by every one of the subwoofers that this produces a lot of phase offset, and this phase offset produces comb filter. Okay, so then if we come back to see this, right now we understand the consequences of the directivity according to the array length, and that the distance between subwoofers individually by only two speakers also has directivity. So doing an array, it's more of the same. But now let's see arc of subwoofers. In this case, what we will do with the arcs of subwoofers is that we will have sections of circumference. And in order that you can understand what is a section of circumference, it is this. I will have here an array. You can see here all the speakers are in the border of this circle. In the border of this circle, we have the array of speakers. The distance between the speakers is the same, 2.5 meters individually. This speakers is 2.5 meters, but now we are producing an arc section of 60 degrees, and this 60 degrees is from the focal point going in the direction of the last speaker and the focal point to the opposite speaker. So this is the section that measures 60 degrees. What is important to understand for us is that this focal point is 17 meters radius. So the distance from the center, where all the speakers will be identical in distance because they are in the border of the circle, is 17 meters. What happens if we make, instead of 60-degree arc, 50-degree arc? Then what happens with 50-degree arc, let's wait for here to be displayed. It is resisting, but okay, it's here. So you can see that with 50 degree, what happens is that now from the new radius that now is not at 17 meters but at 20 meters, we have equal distance from all the speakers in this section of the circle, and radius is 20 meters, and the total angle from this last one to this last one is 50 degree. Now let's do 40 degree. With 40 degree, then what we will see is that the radius will go more far away. Let's see what will be the new radius for doing this 40 degree. Okay, it says 25 meter radius. So we are going from 17 to 20 to 25, and now the portion of the circle is smaller than before because this circle is larger in radius. So this is a 40 degree section. Let's see a 30 degree section. In this case, 30 degree section. Let's wait for this to be ready. Come on, come on. And the radius will be even more. You can see now that is 33 meters radius. So this is a circle that is larger than before, and the portion of the circle that we are using is smaller. And still, the line measures 17.5 meters from the first to the last one. And what is the section of the circle? 30 degrees. So this is from here to here. Then let's do a 20 degree. And 20 degree will have the radius even far away. So this means that the center of the circumference will be even more far away. Let's see how much far away will be that. Okay. Now we have 50 meters radius. So in order to see the focal point, now we are more far, and you can see that the circle is going outside the scale that we are watching. And the last example that we will do is the one that is 10 degree, okay? Let me wait for this to be ready to click, because I can see that. Now it's ready. Okay, so now you can see, oh, the center of this is very far away. How far away? Is 100 meters. This is the focal point. And compared to the circumference, now we are using a very small portion of the total circumference. So if we change this and go back to the 60-degree arc, now you can see that because the circumference is smaller, we are using more portion of circumference. Well, now let me call here, that is the plan view. And in order to summarize this, we can see now that the 10-degree circumference is 100 meter focal point. A 20 degree of section of the circumference is 50 meters focal point. Then the 30 degree section of arc is 30 meters focal point. 40 degree, 25 meter focal point, 50 degree, 20 meter focal point, and 60 degree section of circumference is 17 meter focal point. What we can understand now is that the more section of circumference that we want to use, the focal point goes closer. So it's very important that you understand that in order to accommodate this in the circle, what I have used is a calculator made by Merlin Bambin, where this calculator basically will give us the coordinates x and y position for the subwoofers. In this case, you can see that the spacing between the subwoofers is 2.5 meters, and I have 8 subwoofers. And you can see here in the right that every little box here is each one of the subwoofers that is being deployed. Now, if I do here 10 degree arc, what you can see here is that the focal point is all the way here in the back, and it says that is 100 meters back. Okay, and the relative positions of every one of the subwoofers in the displacements to the back, it says that the center one is 1 centimeter back, the next one is 7, 19, and 38. So this means that this design that is the 10 degree is this one, and basically this is the guy that is 1 centimeter back, this is 7, this is 19, and this is 36 centimeter back. If I go and select that, instead of doing the 10 degree, I do the 30 degree, the displacement is more. And this displacement in the calculator by Merlin is called Subwoofer Array Designer. In the Subwoofer Array Designer, if I do 30, you can see that displacement to the back increases. Now the lateral ones is 1.14 meters. So in other words, the ones that we have here is 1.14 meters back compared to the center one. And if I go to the larger circle, okay, this is the one, the displacement now is more large. And this displacement, if I do here 60 degree, then it's telling me the values. 2.24 meters back is the center, is the outer one. So this means that this is 2.24 meters back. And in order to build this, I was using the values indicated by this calculator. Okay. In another video, we will explain that constructing straight lines with electronic delays from the center to the outer, basically what we'll do is simulate the straight line that is these black dots here, and to simulate the arc shape that you see with these lines, white color. And in this calculator, we have the electronic delays that the center ones are having less delay and the outer ones will have more delay. So if we use, in this example, 4 channels electronic delays from the center to the outers and patch by pairs, what we will have is this directivity pattern. And if I change to physical arc will have more narrow in the back, directivity narrow in the back, but wide in the front. And this is because the focal point is the point where all the speakers arrive at the same distance and same time. So this means that this is where all together have maximum summation. But when we use electronic delay, what happens is that the speakers are in the same position, and the electronic delay in reality is latency. So the latency affects both directions. For this reason, if you use electronic delay, we don't have a concentration of power here in the back in the center, but it spread the back as well as the front. But remember, this is another video. Okay, coming back in this explanation, then this is another thing that we need to understand with the subwoofers design in a configuration that it is arc shape. And the explanation goes this way. If I select here the 10 degree, okay, it's very important to understand that the 10-degree arc, it is this line versus this line. So these two thick lines is the 10 degree. However, in this position, the directivity variation center to the outer will be more than 6 decibels. So if I go here and test this one, let me clear all my previous traces for this new explanation and do this. So now I am in the center, and if I put this microphone exactly in the line that it's in the direction of the 10 degree, okay, it's here. What we will see is that we will have, compared to the center, more than 6 decibel variation. And according to this scale, we have here around 10 decibel variation, and here also like 8 or 9 decibel variation. So this means that the 10 degree is outside the coverage. And this is something important to understand. The usable coverage is 2/3, 2 divided by 3, 2/3 of the angular value of your array. So if your array is 10 degree, 2/3 multiplied by 10 degree is 6.66. The 6.66 in this case, it is this one. This is 67% of the coverage. So the 100% of the coverage in this case is 10 degree, but 6.7 degree is 2/3. So now what we will do is locate the microphone, locate this microphone in this line. This line is the 2/3. So this means that now when we are here, we can see that the variation that we have, you can see 95.5 versus 101. This is 6 decibels. So the maximum variation that we will have in any given frequency in the bandwidth will be 6 decibels or even less. So the usable directivity from point of view of system design, it is 67% of the angle of our system. If I do now 30-degree system, and we come back to the microphone in the center and we test again at this system, let me go delete this trace. Okay, so now this is center microphone, recall here, and now select this microphone, and if we come here, let's move this microphone to the 100%, so this means to the 30-degree limit. 17.5. Okay, it's here, and what we will see is that the variation at some frequencies is more than 6 decibels. This is more than 6 decibels. This is more than 6 decibels. But if we want to be contained before the 6 decibels, is this is 67% of the 30 degree. That basically this is 20 degree. then you can see that the variation, you can see 94 versus 100 is 6 decibels. So the area that shows maximum variation will be in the limit of 6 decibels. If I go to another one, let's do the 60-degree system. Okay, so now select the center microphone and come back here and store this center of 60-degree and recall here. So this is the center of 60-degree. What happens if we go here and now put the microphone exactly at 67% of the total? That means 67% of 60 is 2 thirds of 60 is 40 degrees. So this means from this center, 40 degrees from here to here. Okay, so now we will see that the variations will be contained in less than 6 decibels. Around here is 4 decibels, and here around here is 4 decibels. So we are good enough. But as soon as we go in the direction of the 100% of the coverage, now this will be more than 6 decibels. So this is outside coverage. So this is the other important thing to understand then when you are doing a design of a subwoofers with electronic delay or physical arc shape. When you are doing your designs, what you have to understand is the fact that your total coverage is not what you think. Your total coverage, it is 67% or 2 thirds of the arc shape. So now if we come back here and see our index, we can learn that everything about the sections of circumference and the focal point is being explained. And let's go to understand what happens with the frequency response according to the directional angle. Okay, so let me go back here, select a microphone around this guy, the 30 meters, and select the system that is a straight line. This is the straight line, and this is only one speaker. You can see that this is the response of single speaker. Let me do delete and store one speaker. Okay, this is only one speaker. And here, what happens if we play 2 speakers? Well, we know that 2 speakers should add in the same position 6 decibels. Is this, and I can do an offset in the blue trace, that is the new trace, and you can see that here shows that it's exactly 6 decibels. Okay, but if we make 2 times more speakers, another 4, this should be then now 2 times 6 is 12 decibels. So let me come back here. Okay, 12 decibel of increase when we have 4 times the speakers. And what happens if we add all of them? Well, it should be 18. But now something happens, because if we try to see with 18 here, you can see that not even the lower frequencies increase 18, and in the higher frequencies increase even less than the 18. The reason for this goes because if we are in this microphone and we understand that the trajectory of the center ones is shorter, the trajectory of the outer ones is larger, and everyone goes to the outer is slightly larger, the larger trajectories produce a little bit of phase offset, and this phase offset will decrease the capacity of summation. Also, we have inverse score law, and the outer ones traveling more distance. In this point where we have the microphone, we receive a little bit less level from the outer ones compared to the center ones. So the frequency response will be changed, but will be changed dramatically from the position that we are. Let me show you. So this is what happens if we are very far away. Let me go to the 85 meters in the center. 85 meters in the center shows the frequency response is very good. But what about 45 meters in the center? Drop of high frequencies a little bit. What about of 5 meters in the center? Whoa, the frequency has a lot of deformation. Why? Because if you are at 5 meters, think about this. At 5 meters distance, the trajectories are very different. The outer ones travel more distance, but also the outer one, the distance is like 2 times the center one. So this means that the outer one is arriving to this destination by 6 decibels less than the center one. And this will make that the outer one has less contribution of summation when you are closer to the system. So the frequency response changes depends in how far you are. If we have only 2 speakers, then the frequency response will not change. In other words, if I select only 2 speakers, the response will be perfectly flat at 5 meters or at 45 meters or, but I think that here, this is all speakers, so I have to select the center ones. Okay, so you can see it's perfectly flat, and if I go to 85 meters and select only the center ones, you can see that it's perfectly flat. With only 2 speakers, they arrive at the same time distance, so this means that this is no problem. But at long distance, all the speakers together, you have a small deviation in the response, but the closer you are, the response start to have, this is the second microphone, is the center microphone. The response start to show a little bit of deviation. So the closer you are, more deviation. It's important to understand then that the portion of frequencies that pays more price for the summation of all the subwoofer system is the higher frequencies. And this is logical because the higher frequencies are the ones that has a smaller wavelength or a smaller time period. And this is the one that by phase differences can have less summation. Okay, so the part of understanding that and now the directivity angles versus the frequency response. Look at this, but let's take the microphone 30 meters. And let's see at 30 meters what is the response of all the speakers. You can see this little attenuation. Okay, let me store, and this is the array at 0 degree. What happens if we change to the array that is 10 degree? So this array is a section of 10 degree that has very little displacement to the back. In the outer speakers, you can see a little bit of drop. This is the drop when you have 10 degree arc. What happens if you have 20 degree arc? Well, the drop is more dramatic. What about if you have 40 degree arc? The drop is more bandwidth, and even the lower frequencies cannot have the maximum summation that you have at 0 degree. And what about 50 degree? At 50 degree, you have more portion of frequencies with lack of summation, and at 60 degree, you have even more lack of summation. So in other words, now that we are in the position 30 meters here, with the system that is 60 degree arc, is where you have less summation. And what is the lack of summation? Well, if we display this to see like the average of the variations, it's around 6 decibels less, 6 to 7 decibels less than when we was at 0 degree. This is the other important thing to understand. If we see what is the response of this array, like in the central frequency, we can understand that the response in this system will be contained from here to here. This is the maximum level, so this is where we can say we have summation. And in this area, I will use the symbol minus, that is, we will have the attenuation, or comb filter. So let's go here and let's see. This is what happens now. But what happens when we start to do arc shapes? Let me go to 20 degree. And now, in order to have more energy lateral, the central area will drop summation. And the more you want to go in the arc, you are sending more energy to the outside. You will have less level in the center. That is what we have been watching here. And if we do the maximum arc for this explanation, we cover all the area, but in order to cover all the area, now we are subtracting energy in the central area to pass energy to the outside. So look at this. Let's put this in colors and pay attention to the scale. I will put a mark, let's say here in the back. Remove these symbols. Here in the back we have this color that if we compare the level variation, this bright yellow, we have one color less, two color less. So this is that we are around minus 21 decibel from the maximum level. This is minus 21, it's here. And let me mark like these two positions of level change. What happens if we do 20 degree? Let's wait for this to reestablish. Okay, when we have 20 degree, it's recall. Yeah, it's doing. Okay, you can see now that this yellow goes here and this goes here. Still, this is like in similar level, but now we do, instead of 20 degree, let's do 40 degree. And let's wait this to reestablish. Okay, and as soon as we do 40 degree, let's see how the level will drop. So now the yellow moves here and the second yellow green moves here, and now we are in the next color, so we drop to minus 24. And then if we go to the section that will be 60 degree, we will see how the level in the distance drops more. So 60 degree, doing this, and let's wait for the result. Okay, and look at this. Now this moves from here to here, this moves from here to here, and we drop from this color one color more, two color more. So now we drop 6 decibels more compared to when we was at 0 degree. So we cover more area, but the price to pay is less level. We can see this with the microphone. Okay, so now select one of the microphones. Okay, let me remove all the previous traces. Okay, take the microphone in the center, central microphone, and in the central microphone, let me do the system 0 degree. Actually, I want to measure from the center to the outer. Yeah, I will do this at 45 meters. Okay, here I will measure all of them. And let me do, okay, center microphone. It is center microphone. Let's recall here. But what happens if I go to the outer microphone? It's comb filter area. Okay. So this is the outer microphone. And the outer microphone, let's recall here. So this is the comb filter area. And the system is 0 degree. What happens now if the system is 20 degree? Well, with 20 degree, in the center microphone, okay, the level drops a little bit. Oh, the level drops a little bit as soon as we have 20 degree arc. What happens in the outer mic? The level cancel less, so the comb filter is decreasing. And what happens if we have a 40 degree arc in the center microphone? You can see that the level drops more and in the outer microphone, the level increases even more. So if we go to the 60-degree system, in the center microphone, we drop more. Let me store this. This is the center at 60 degree. And recall here. And what is the outer at 60 degree? Is this one. So this is the outer at 60 degree. So what we can understand here is that these two guys, it is center and outer at 0 degree. And these guys are center and outer, the same microphone position, with 60-degree arc. So you can see that they are going closer in a way that we are in the requirement of less than 6 decibel variation at any given frequency. And then we can understand that doing arcs is taking out level or SPL of pascals or acoustical pressure from the center that goes from this red to this blue, and is making that the outer that has less has more. Normally, I use the expression in this case to be like Robin Hood. Robin Hood that is taking out money from the guy that has more money and give to the guy that has less money. So then this is having better distribution in all the area, but the price to pay for doing this is less SPL in the central area. That's very important to understand that. So now we can understand the directivity effects in the final SPL, and the last part of this explanation is about the summation of the subwoofers if you are in the near field or in the far field. And something that I have to clarify here is that we are watching these graphics of colors from the point of view of attenuation. But now we can read here in this area that I am clicking here that the maximum level encounter here is 102 decibels. So I will make that the colors now is SPL. So now the red color is 102 decibels. And we can see that we are around 81, 70, 87 is this. This portion is 87, then this portion is 82, this portion is 81. Okay, so let me do this. This portion is 81 decibels. It's here, 81. What happens if I have more display angle? Oh, take out this and go like this. As soon as I do more display angle, what will be the SPL here? Now this is from this yellow 1, 2, 3. 1, 2, 3. Now the level is 78. So the new level is 78. The level is dropping in the far when we have more arc shape. And now if we are going here, we are lower than 78, that is 75. So we are moving from a straight line 80 at this frequency 63 from 81 decibel to 75 decibels. So this is what we can see here. But what happens in the near field? In the near field, this means that we are here close, here around 5 meters. Let's see the colors around here. So the color that we have here is the bright red. That means 102 decibels. So 102 decibels, let me use an arrow to mark here 102. Okay, what happens if we go and have 30-degree arc? Okay, with 30-degree arc, we can see that the color is the same, 102. So in the near field, the level is not really changing. And what happens if we go to the 60-degree arc, well, in the near field, it's the same red color. It's 102 decibels. So having arc shapes or a straight line in the near field is not having consequence. But pay attention on this. If I go to the microphone 5 meter in the center, and now with 5 meter in the center, and clear all of this. Clear. Okay. And we have 5 meter in the center. Select only the center two speakers, this guy and this guy. You will see that this is two speakers at 0 degree. Okay, what happens if we have 4 speakers? So the 4 in the center that you can see here. With these 4 speakers, now you can see that the level is not increasing so much, and even in the lower frequencies, 1, 2, 3, it's only 4 decibels of increase. It's not 6 decibels. And if we add another 4 speakers, the level basically it's similar to 2 speakers. The level here is 2 speakers, a little bit more than 2, a little bit more than 2, and less than 2. So this means that here in the near field, we have an array of 8 speakers, and we are increasing like if we have only 2. Why? Because phase differences and because the lateral speakers traveling to this position is so much, so this is a lot of inverse score low attenuation. So this means that they cannot have so much summation in the near field. But what happens if we are at longer distance? The situation will be different because the trajectories will be different. Let me do at 0 degree to see again the same thing. 2 speakers at 0 degree, that is the number 1 here, and the number 1 is the same graphic as before. But let's make now 4 speakers. Now you can see that with 0 degree, the lower frequencies will be closer to the 6 decibels. In this case, you can see that it's 5 decibels, but the high frequencies is the one that has less summation because shorter wavelengths are affected by the distance more dramatically than longer wavelengths. Now we have 6 speakers, and now we have all speakers, and you can see that even when we have an straight array, the increasing level is not really there. The level is similar to only 2 speakers. So the level is similar to only 2 speakers if your array is straight or in arc or in arc shape in the near field. But what happens if we go to the far field? In this case, let's select the microphone in the center 85 meters. With 85 meters, if we select only 2 speakers, this guy and this guy, we will see less level than before, of course, because we travel so much. So store, this is 85 meters, 2 speakers, okay? This is our reference speaker. If we have the next 2 speakers, that is the number 2, the level will increase perfectly 6 decibels at all frequencies. 6 decibels. Why? Because the difference in trajectories from these 4 speakers at here 85 meters, it's so small that for all the frequencies wavelength from, in this case, 60 to 100 something, they have summation. What happens if we have all speakers together? Then you have the approximation of the 18 decibels. Okay, this is this is 12 decibels because we start with 2 speakers. Okay, so you can see that the only portion that has less summation is the very high frequency. So why? Because comparing the center speakers here in the back, the outer speakers travel slightly more, but not so much. The consequence will be more dramatic with a 60-degree arc, because with 60-degree arc, we will have more relative phase shift. So now, if we select the central 2 speakers, it's the same as with no arc, the same. But as soon as we start to have more speakers, the summation will not be exactly the same. Let me drop 6 decibels. Okay, you can see here the very high frequencies is not really there. And if we have all the speakers, then the summation is gone in the higher frequencies. So this is minus 12. Only the lower frequencies, and even the lower frequencies don't reach the 12 decibels because all the phase differences by the construction of the arc shape that is moving the speakers back, then this is making that you cannot reach all the summation in the arc compared to straight line. So you can see that in the near field, the array of subwoofers is not very effective in summation because the tremendous relative distances by everyone in the array, but in the far field, these difference in distances are smaller. Well, thank you very much, and remember that there will be other videos explaining different topics. In one of the videos, we will explain the transformation of the arc shape to a straight line with virtual arc by electronic delays. And in other videos, we will explain the differences or the variations in coverage by using straight lines, arc lines, and two more designs. One is called M-fided and the other is called gradient. Thank you very much.